expectation value is basically if I perform some kind of random event or trial experiment a bunch of times, on average, what do I expect the outcome to be? Okay, so we're going to look at this through the context of a dice game. We're going to say that you are going to pay $50 to play this game. Okay, now if you roll a 6, you win $1 and you get back your 50. If you roll a 2 or a 4, you win $10 and you also get back your 50. But if you roll a 1, 3, or a 5, you get nothing, and you do not get back your $50, because that wouldn't make a whole lot of sense. So I'm going to list the different outcomes. 1, 2, 3, 4, 5, 6 are the different outcomes. And then what do I end up netting in terms of money as a result of rolling these things? So if I roll a 1, I lose $50 because I don't get anything back. I paid 50 and I get nothing. If I roll a 2, I get $10, right? I leave with my $50 and then 10 more than what I started with. 3, again, negative 50. 4 is going to be the same as 2. I net $10. 5, I lose $50. And for 6, I actually want to make 6 the grand prize. So let's say that instead 6 is 100, not 1. We want 6 to be a nice, good, big prize. So for 6, I get $100. Okay, so I'm going to say, well, if I add all these things up, the total I get is negative $30. And then if I divide this by 6, I end up getting negative $5. So what this is saying is that on average, I expect to lose $5 per game. Now, obviously, I can't really, there's no option here that lets me actually lose $5, right? But let's say I play this game 10,000 times. If I did that, I would expect to lose $50,000, right? Through combinations of, losing 50 here, gaining 10 here, losing 50, gaining 100, then losing a bunch. I end up netting negative $5 per game that I play, okay? But to get a more kind of empirical way of writing this, let's look at what exactly we did and rearrange a little bit. So I said that the EV, or the expected value, is negative 50, and all this is dollars. I'm just going to drop that sign though. Plus 10 minus 50, plus 10 minus 50, plus 100, and we divided that by 6, right? We divided by the total number. So I'm going to split this up a little bit, and I'm going to say, oh, well, I have 3 ways of getting losing $50, plus 2 ways of winning 10, plus 1 way of getting 100. Okay, then you have to divide it by 6. So then I can split this and say, hey, this is 3/6 times negative 50, plus 2/6 times 10, plus 1/6 times 100. Okay, so what I've done here really is I've said, oh, my expected value is equal to the probability of event 1 happening times the payoff associated with event 1. And now it's not always going to be a payoff, it's not always going to be money, but basically the value of that outcome, right? And then we have plus the probability of event 2 times the payoff for 2. And we keep on doing this until we hit the probability of n happening multiplied by the payoff of n. I don't know why this is so shaky. Okay. So another way of writing this, if we use summation notation, is we can say that the expected value is going to be equal to the sum from 1 to n of the probability I times the payoff of I. Okay. Now, if you haven't seen this notation before, that's okay. All this notation means is you are basically plugging in the value of I first, so 1. And then after you do that, you add to that 1 plus 1. So then you have 2, and then 3, and then 4. And you keep going until you hit whatever n is. So like, for example, if I said, what's the sum from I is 1 to 3 of x, right? Or, sorry, I. then this would be, okay, well, I is 1, so I have 1, and then plus 2, plus 3. Oh, I hit my upper bound, we stop. I get 6. Okay? And you can see that's just what we have here, right? 1, 2, and then 3, 4, 5, 6, all the way until we hit n. Okay? So let's do another example with this. So I'm just going to clear out everything here. And we're going to say that we are doing a basketball toss. Okay? So this basketball toss costs $50 to enter, just like the dice game. And you get 3 shots to get a basket in. The probability of getting 1 basket in is equal to 0.3. Okay? So if I just throw a basketball into the hoop, I'm going to get it in 30% of the time. Now, the reason it's so low is because these games are all rigged, right, to favor the house. That maybe the rim is a kind of elliptical shape, or it's smaller or extra bouncy. You know, there's a whole bunch of ways to do this. So the prize payout, depending on how many baskets you get, looks like this. If you get 0 baskets, then you get nothing. If you got 1 basket, you win $5. You don't get your 50 back, you just win 5. If you get 2 baskets, you get $60. So you net 10 here. And if you win 3 baskets, you get all 3 in, you win $250. Okay? And I want to know, what's the EV of this game? What's the expected value of this game? So I know what all the outcomes are, right? I know how much I'm going to net for each one, but I don't know what the probability of getting 0, 1, 2, or 3 is, right? Now you might say, oh, well, you know the probability of 1, it's 0.3. No, because it's 0.3 for 1 shot, but I have 3 chances to get 1 shot in, so we have to account for that. So what I'm going to do to set this up is I'm going to calculate each of these probabilities. Say the probability of getting 0 shots, probability of getting 1 shot, 2 shots, and 3 shots. Okay? So the probability of getting 0 shots means I miss everything. And to miss everything, that's going to be 0.7 times 0.7 times 0.7. Hey, 0.3 to the 0, 0.7 to the 3, oh, this is a binomial distribution, right? So if you haven't checked out I think the previous video where we talked about binomial distribution, definitely go and look that over. So this is a binomial distribution, which means we have 3 choose 0 ways of arranging this, right? We only have 1 way of arranging 3 losses, times 0.3 to the 0, because we have no wins, times 0.7 to the 3, because that's how many losses we have. If we do that out, we get 0.343. For getting 1, so we have 0.3, we get 1 basket in, we miss 2 baskets. How many ways can we arrange that? It's going to be 3 choose 1. Or you can do 3 choose 2. It's going to be the same thing. That's going to be equal to 0.441. Next, we have 3 choose 2 times 0.3 squared times 0.7 to the first, sorry, and that's going to be equal to 0.189. And finally, we have 3 choose 3 times 0.7 raised to the third. So, oh no, sorry, I mixed this up. My bad. I want to keep everything in the same order. Just to make it look nice. So this is actually 0.3 to the third, not 0.7, times 0.7 to the 0. So we get all 3 shots in, we don't miss anything. And the probability of that happening is 0.027. So you can see, once again, most people, 70% of people, are going to get 0 or 1 shot in. The tail end, again, of the binomial distribution is very small. So now we can calculate the expected value. So the expected value is the probability of getting 0 times the payoff of 0, which is 0, plus the probability of getting 1 times the payoff of 1, which is negative 45. And then you're going to say plus the payoff of getting 2, or sorry, the probability of getting 2 times the payoff of getting 2, which is $10. Plus the probability of getting all 3 shots in times the payoff, which is $250. And if we plug all of these things in, you're going to have, you're just taking these numbers and putting them in. So you're going to have 0.343 times 0 plus 0.441 times negative 45. That's totally 45. Plus 0.189 times, where am I, 10, plus 0.027 times 250. And when you do all this stuff out, you get that the expected number of baskets, or sorry, the expected outcome, the amount of money that you expect to net, is negative $29 and 705, so about 71 cents. So it is a really bad idea to play this game. These games, right? It looks appealing because you're like, oh, for 3, I'm like, multiplying my money by 5, which is great. But the probability goes down enormously when you get to this point, right? 2% or 3% of people are going to end up getting 3 baskets in, which means that the house is going to net a huge amount of money. So it's always good to calculate the expected value of games if you're playing games, and you can use expected value to do a lot of things that are really useful in the real world. So that is expectation value.